All right, we continue with non-calculator multiple choice problems. We have three of them. And the first one is the integral of arctan. And this is going to be an integration by parts problem. I always say that if you see how to differentiate a function, but you have no idea how to integrate a function, that means you need to do parts where you're multiplying by a dv of 1, which is easy to integrate to x. And you do know how to differentiate arctan because that differentiates to du equals 1 over 1 plus x squared dx. So when I do uv, I get x times the arctan of x, that's here, minus the integral of v du, so x over 1 plus x squared. This section here, the integral, becomes a u sub problem with your u equal to x and, with your u equal to what's in the denominator, u equals 1 plus x squared, and du equals 2x dx. And you don't need the 2, you just have a single x over here. So we're going to actually divide by 2 on both sides. So I end up with a 1/2 out in front, and that's what I've done right here. I put a 1/2 out in front and then 1 over u du. And 1 over u integrates to the natural log of the absolute value of u. I went ahead and subbed in the 1 plus x squared from my u substitution. That's coming right back in there. And then, of course, you carry down the x arctan of x, which I put in with that arrow, but really because I'm just matching to the answer, I just did the arrow to save a moment of time. So I have x arctan of x minus 1/2 ln of the absolute value of 1 plus x squared plus c. This matches to E, and I'll take a moment to point out that they did not use the absolute value on 1 plus x squared, and you're allowed to do this only in the case where the expression cannot possibly be negative. So 1 plus x squared, since x squared has a domain of greater than or equal to 0, the whole expression then would be greater than or equal to 1, which is okay within the natural log domain. Okay, number 11 is an arc length problem. And it might be useful to draw a picture here. We have y squared equals x cubed, and then the line x equals 4. So if I draw in the line x equals 4, it's here. Now, if I square root both sides, I'll have y equals the plus or minus square root of x to the 3/2. I think we're going to get this thing that looks like a bird flying right here. So the question is, okay, hang on, I just hit pause and came back. It is a bird flying, but I put it in the wrong quadrant. So let me fix that. This is just our x-axis. The bird flying is partially here and partially here. And this is important because you want the arc length of this curve cut off by the line x equals 4. So it's this and this. So what we can actually do is just find the one arc length up here and double it. So this curve is y equals x to the 3/2. And if I set up a situation where I'm integrating that from 0 to 4, and I double that integral in order to get this part and this part of the curve. So I then need 1 plus the derivative here squared. So the derivative of y is y prime, which will be 3/2 x to the 1/2. So when I square 3/2, I get 9/4, and when I square x to the 1/2, I get x. And I end up with a pretty tricky integration problem. It's doable, but I'm going to need u substitution to do it. So I'm going to I'll work over here. My u is underneath my inside function, 1 plus 9/4 x, and my du will just be 9/4 dx. And I don't need that 9/4, so I end up multiplying by 4/9 on the outside. So 4/9 times 2 is 8/9 here, and then I have the square root of u du. And then my limits of integration are going to change, or it looks like what I did in this work here is that I converted back with u substitution, which is fine. So I will integrate rad u. That's going to integrate, I have 8/9, and that integrates to u to the 3/2 times 2/3. So 2/3 u to the 3/2. And I believe that's where I came in back over here. I said, let's switch it back to 1 plus 9/4 x instead of u, and I have the 3/2 here, here's my 2/3, here's my 2, and here's my 4/9. And I got that 8/9 by multiplying through, but this brings me right back, matches here. And then I plug in, and then I use my original limits of integration from 0 to 4. If I plug in 4, this nicely just goes to 9, so 1 plus 9 to the 3/2. And then plug in 0, I get 1 to the 3/2, which is right here. Notice that from this step to this step, I multiplied through the 2 times the 2/3 times the 4/9, and I got 4 times 4 is 16 over 27. That's right here. So then I end up with 16 over 27 times 10 to the 3/2 minus 1 to the 3/2. So that's this, and it looks like that exactly matches choice C. So for number 12, we actually have an improper integral. So I set up the improper integral, and I'm taking the limit as t goes to infinity and t replaced infinity as my upper limit of integration. Then I can integrate e to the negative x goes to negative e to the negative x. And evaluate that from 0 to t, I get negative e to the negative t minus a negative, so plus e to the negative 0. E to the 0 is just 1. What you need to see is that negative e to the negative t is really negative 1 over e to the t, and then plus 1 over e to the 0. When I plug in infinity into this t in the denominator, this first term goes to 0, and the second term just goes to 1, so my answer is 1.